All right, so as always, feel free to drop any questions that you may have in the chat. Um, and otherwise, we're just going to get started. So today we're going to be going over, spending most of our time going over containers and the various sorting algorithms. And then we're also going to be talking a little bit about binary search. That's going to be most of today. Going over announcements. Remember, project 2 is due a little bit over a week from today. So if you haven't gotten started on that, I would highly, highly recommend it. Remember, the project has 2 parts, so that can sometimes take people by surprise that the minus gate portion is not the only portion. You have to do part B with the priority queues as well. So then also for the lab 4 auto grader, that's going to be due Friday. The handwritten problem for this lab is also due Friday. And then the quiz for this lab is due the following week. And there is no auto grader portion for this lab. So you guys get a bit of a break for that. So there are those announcements. Otherwise, the midterm is coming up. We said on the slides that time is TBD, but I actually think that that is no longer true. We have 3 times for the midterm, so we split it up into 3 different times: 9 a.m., 6:30 p.m., and 11 p.m. So 9 a.m., 6:30 p.m., and 11 p.m. are going to be 3 times. The midterm was on the 21st. I think that the midterm is on the 21st. Yeah, we do have it on the 21st. That must be, I was not responsible for these lab slides. The slides must be outdated. Yeah, from my understanding, I would check the schedule to make sure about that. But from the Piazza post, I think it is on the 21st, not the 20th. But those are the 3 different times. Thank you for that catch, Elizabeth. But those are the 3 different times. Make sure the Piazza post it should be pinned to the top. It has a Google form. Make sure to fill out that Google form to state which of the 3 times you'd prefer for taking the exam. We need you to fill that out so that we can assign everyone to the proper times. Otherwise, we'll be having a in-class review session. So definitely would recommend attending that. Those are usually a great way to get some practice. Otherwise, we have for alternate time and SSD accommodations, make sure to fill out the request form. And yeah, so that's pretty much that in terms of the midterm. Any questions about the midterm, about any of the announcements before we move on to the agenda for today? Is this the last lab before the midterm? I believe so. Don't quote me on that, but if you check the schedule, we usually don't have labs the week of the midterm. So I think that this will be the last lab before the midterm, yeah. Any other questions? Yeah, it is. Yeah, thanks for that confirmation there. So that's also why this lab doesn't have a auto grader portion, is to give you guys some more time to wrap up the project and then start really studying for the midterm. And I would definitely recommend taking time to go to the review session and do the practice exam that we give you guys for these, because typically in this class, most students, I would say, get fairly decent grades on the projects, and most of the labs, as long as you don't, as long as you're all right with your time management, and the midterm and the final are often where the different points fall and stuff like that. Will the exam be on Crabster? I'm not certain yet how we will be doing the exam. I believe it's through Canvas. Usually we post, how many practice exams do we get for the midterm? Usually we post a single practice exam for the midterm. So unfortunately we just post one. That's because sometimes the staff will reuse old questions for the midterm. So we try to avoid posting several. So unfortunately, you guys will only get one. But I believe it'll be on Canvas. That's how we have it set up. And then for the coding portion for the written problems, those are usually submitted through Gradescope, kind of like how you've been doing your handwritten labs. Best way to study for the exams. The exams aren't like, definitely, like, I guess the number one is to do the practice exam, but that's kind of a given that most students will do that. I've found things that really worked for me are doing the practice exam, then also going through all of the, like, the lecture material, the discussion material, making yourself. I know that this exam, because we're online, it's going to be kind of more open note, but still going through the time to make yourself a cheat sheet, like a 2-page cheat sheet, is in of itself pretty, I think, useful studying, because you have to kind of remember all that information if you're writing it down. I would definitely recommend actually writing that information down. Don't like copy and paste it, because I think that you're going to have better retention if you're writing it down, and that requires you to just go through all the lecture and lab material. I think that's a pretty good way to study. Otherwise, in the past, we've sometimes released extra practice questions that are kind of related to the exam content. I'm not certain if we'll be releasing those this semester, but just keep an eye out for those. If we do, those are also a great way to study. And then also attending the midterm review session, there will usually be some more going over some content, and there will be more practice questions there as well. So I'd recommend attend that, or at the very least, watch the recording and try and go through those practice problems on your own. So, and then also just like reviewing your old lab material. The last quizzes on the prior labs, those are kind of going to be similar to the types of questions that you'll see on the exam. So just kind of going over those, checking your answers, maybe attending office hours. Office hours are really useful for that. So, all right. Any more questions about the exam, the midterm? All right, cool. I don't see anything. So I'm just going to jump into the material for this week. So we'll be kind of just going over midterm topics real quick, then just getting into containers and sorting, and then binary search. So for the midterm, topics to review, pretty much anything that we have covered in lecture and lab so far is fair game. So that's, complexity, runtime analysis, recursion, and the master theorem. So these were kind of like the first topics we covered. All sorts of ADTs and containers, anything to do with the STL. You can typically guarantee that there will, I can't, confirm this, but there's usually at least one handwritten problem that has something to do with the STL. So I would definitely recommend just brushing up on, really you get a lot of practice with using the STL through the projects, but just understanding the different types and, complexities and how to implement, or not really how to implement, but how to use the different like member functions of the various classes in the STL, is definitely an important thing to study up on. Stacks, queues, and priority queues. We did a lot of these with the projects, but still just kind of understanding them from a conceptual standpoint is important. Ordered arrays, so understanding like the different algorithms with ordered arrays. Then also similar to that, set operations with the union and intersection and union find. So kind of what we went over last lab. the elementary sorts and then the library sorts, which is what we're going to be going over this lab. Quick sort and merge sort, also going over this lab. Heaps and heap sort, we went over that last lab. And then linear time sorting algorithms. The handwritten problem for this week is kind of going to be related to that, and then also string algorithms and the various string functions. I think you guys had lots of opportunities to work with this from project 1. So maybe just kind of reviewing your code and the concepts behind project 1 would be pretty useful there. So those are basically all the topics to review. Like I said, if you're reviewing things, probably the best way to get the topics down, as opposed from doing practice problems, from my experience, is go over the labs in the lecture, and really just take extra notes. I think taking the time to write that cheat sheet for yourself, and you can kind of divide it up based on all of these various topics here. And then just writing down notes for each topic is a really great way to study and brush up on all of this material. So, all right. Moving on. If there are no questions in the chat about the topics for the exam, we'll move on to containers. Good question. Have a question here. For private questions, I'll make sure to I'll make sure to take time to answer those at the end of lab. Usually I have a few extra minutes if I wrap up early, and then I can kind of take a bit of time and take a look at that. So otherwise, if there's no other questions, let's move on to containers. So we have different types of containers. There are searchable containers, such as vectors, decks, and lists, and then not searchable containers, stacks and queues, right? So the important thing to kind of understand here is that for stacks and queues, we have like our top function, right? So you can usually only access one element. You can't necessarily access elements throughout. And then sequential, which allows us some form of iteration over the elements, right? So you can take a pointer and you can kind of walk through all the elements in some order. And then that's basically the same things, right? Stacks and queues are not going to allow kind of sequential walkthroughs through all the elements. So that's basically that, fairly straightforward. We also have sorted and ordered containers, right? So sorted containers are when the elements have some sort of like they're in a. I'm trying not to mix up the vocabulary, but they're in an order. There's a predefined order, right? And so they usually you can like implement a binary search on these, right? So like a sorted array is the classic, and these are you can't do insertions quite as easily into a sorted container, because you need to maintain that invariant, right? Where the elements have some specific predefined order kind of thing, right? But they're really great for searching, because you can typically, cut down on your searching time for these sorts of containers. And then an ordered container is one that maintains the current order, right? So if you are inserting an element anywhere, that's not going to disrupt the order. So like if we have like our typical vector, right, or array, this one doesn't necessarily have to be sorted, but if we say deleted this 1 and replaced it with a 5, right, that doesn't disrupt the ordering of the other elements in this array. So that's kind of like how the ordering works. The key idea is that if a container is ordered, you can insert something anywhere, right? And it doesn't move around or shuffle around the other elements. A sorted container does not usually support this, right? Because if you tried to insert, like, say, if you tried to replace this element and replace it with a 6, right? You can't do that because for our sorted container, that would break our invariant and it would no longer be sorted. So we would have to shuffle around our elements so that we can maintain that invariant, right? So that's kind of the difference between these two types of arrays. So let's go into a quick, well, first let's just kind of go over the complexities real quick. Looks like my table did not show up super great, but that's okay. I think that this is a great table if you guys pull up the lab slides on your own to kind of just, I'm just going to skim over this here. But this is, I think, a great thing to add to a cheat sheet, right? Is to kind of make your own table listing all the different complexities for the different operations, right? And the important thing for, yeah. So I'm just going to skim over that and let you guys kind of go over that on your own time. But moving on to this midterm question here. Which of the following statements is true about the contents of the underlying data vector used to implement a binary heap? So is it ordered and sorted? Is it ordered but not sorted? Is it sorted but not ordered? Or is it neither? Or E, none of the above? So let's, I'll give you guys a second to think through this on your own, and then you guys can feel free to drop what you think the answer is in the chat below, and then we'll go over this question. And to clarify, this is for the binary heap, right? So the kind of tree-like structure that we went over in the last lab. So do you guys think binary heap, the underlying array, do we think that that is which of these? Or sorry, not specifically A, B, C, but which of all of these? Feel free to drop what you guys think the answer is in the chat. We have D question mark. Anyone else want to weigh in? B or D? B, I think. Okay, so a couple of B's. A couple of B's. A few more B's. All right, so let's go over this because I think that this might be helpful. And the answer is actually D. So this one is a little bit tricky. I see that we have a couple of B's. So a couple of people thought that this might be an ordered container, but it's actually neither ordered nor sorted. So maybe a bit of a trick question here, but let's kind of go over real quick why that actually is. So we know that it's not sorted, right? That's, I think, fairly straightforward because we have, right, the important thing, let's make these circles a little bit bigger. Need some chunky circles here. There we go. All right, the important thing for this, these heaps, right, if we have like a min heap like this one, right, is that the top element, right, the root element needs to be of greater significance or greater priority than its children, right? But the children can be in any relation. So this heap is valid, but if we moved around the 2 and the 3, right, and we had 3 and 2, where these would be out of order in the array, right? this heap is still valid because the node, the one, the root node, is still greater. In this case, less than, because this is the min heap, right? Is still greater than each of its children. So that's what's significant here, is that each of these two representations are equally valid, which is why the heap is not sorted, because these within sibling nodes, essentially they can be of different order and still be valid in terms of the heap. So that's why it's not sorted, but I think you guys got that. So why is this not ordered? So why is it not ordered? We're going to look at the reasoning essentially is because ordered means that you can insert an element anywhere, right? But the issue with a heap is that you can't really insert an element anywhere, right? So let's say that we try adding a 9 to this, right? We add the 9 here at the end, just kind of like what we went over in last lab. And for whatever reason, my slides are still kind of wonky, but there's a circle there on that 4. We have this 9 here at the end, but now this is going to break our invariant for our heap, right? Because we need the topmost, the greatest element needs to be on top. So just like with last lab, we're going to have to call fix up on this, and we're going to have to move things around. Right, so we have to fix the heap invariant, moves it up 1, moves it up 2, right? And now we can see the elements were shuffled, right? Because we started off with 8 to 4, and those elements have been moved around. So that's what makes this not ordered, is that you can't just insert an element anywhere and have the underlying array stay the same, right? If you insert an element somewhere, the underlying array may have to change. So then, right, this goes to this. It's not just, if this was ordered, it could be like 8, 2, 4, 9, kind of like that. But that's not what we see, which is why this isn't ordered. And this basically just says the same thing. You had to move around the elements, so. Isn't the relative order still the same? Well, no, right? Because we had to move around these nodes. So like the relative order is looking at this underlying array, right? And originally we had 8, 2, 4 like this. And the 2 came before the 4, right? And now we had to move the 2 down so that we could swap it with the 8. And so now in this array, the 2 is actually coming after the 4. So technically the relative order has changed. But what's significant here is that we had to move around these elements. So basically the idea is, if this was just a vector, right, and it wasn't a heap, we could just put the 9 in anywhere, and we wouldn't have to move around any other elements. So that's kind of why this is not ordered. So are there any other questions about this example? Then I will keep moving on to sorting algorithms, which is pretty much going to be the main chunk of this lab here. So sorting algorithms, things to consider: time complexity, space complexity. These are obviously the big two, right? Recursion, is it tail recursive? If it's not tail recursive, then you're going to have stacks. So how deep is the stack going to go? That's going to actually affect our space complexity as well. Stability, so does it preserve the original order of elements? So like if we had like an array with, say, 2 3s somewhere in here, right? So like this, when we sort this, is this first 3 still going to be in front of the second 3, or could those potentially be swapped? That's kind of what stability means. And then adaptability, does the ordering of the elements, is the sorting algorithm able to kind of optimize based on that, right? So if you have like an array like this, where your array is almost sorted, right? Can you make an optimization there where you only have to swap the 2 with that 3, and then your array is now sorted? Um, so that's basically kind of all the different things we're going to be looking at. And then let's kind of take a overview of all of our different sorts, right? Um, we have our various elementary sorts. These are all pretty much going to be O of n squared for the most part. And then our more advanced sorts, which are usually some form of O of n log n. And then we also provide, if any of you guys are interested, I'm not going to take the time to go look at it now, but we provide a visual that's kind of, I think in my experience, visualizing the sorts is a great way to kind of help me understand them, especially if you can like kind of slow the visual down and just kind of watch the process happening. We're also going to be going over a couple of examples in this lab, so that might help with some of these sorts. But essentially, yeah, those are these are the sorts that we are kind of typically aware of in this lab. We're going to be going over a couple of these today, starting with bubble sort. So if you ever asked a sorting question during an interview, that's just a quote from Obama where he was like, "Don't use bubble sort." And as usual, my slides are kind of wonky, but that's okay. We will just kind of draw in here. So I apologize about the slides, but we're just going to make do. This is actually not that. This is, here we go. And squared, and then worst case and squared, memory of 1, and this is stable, right? So essentially what bubble sort does is we just kind of repeatedly go through the array, and every pass through the array, we bubble up the largest element or the smallest element if you're doing like a minimum sorted array. But for the most part, that's kind of what happened. And then this is stable because we only swap elements with different values, right? So if the elements have the same value, we don't swap. And the best way to kind of adapt this is you can keep a flag that's like sorted. So it's like kind of bool sorted equals like false. And then if you pass through the array and your flag is still false, that means that you didn't make any swaps on the previous pass. And that means you know that your array is already sorted and you can kind of quit out early. So that's kind of the only adaptation that we can make. Otherwise, bubble sort is kind of going to be like our like most elementary of the elementary sorts, I guess. And you typically probably want to avoid using this sort, but we're going to be going over it anyways. Fun little anecdote. I actually, back when I was in EECS 280 for the Euchre project, right, we had to, there was the task where you had to like compare cards, right? And so, because you had like your hand. And so I essentially like implemented a bubble sort in my Euchre project, like on my own. I knew nothing about sorting algorithms. And then I, ended up having very buggy, slow code because I was unaware that my sort was kind of trash. But so yeah, don't use bubble sort for the most part, but we're still going to teach you how to use it if you ever choose to. Bubble sort in action. So I only have the partial slides here, but we can just kind of go through this anyways, because I can just draw things out on here. But essentially, right, we continuously swap each element. We bubble each element up. So on our first pass, we're gonna kind of start with the 53 compared to the 38. Okay, these two need to swap, right? like that, and then we compare it to the 76. Okay, the 76 is larger than the 53, so that's good. Then we compare 76 with the 29. Okay, these two need to swap. Okay, 76 with 61, these two need to swap. 76 with 53, these two need to swap, right? 76 with 14, these two need to swap. 76 with 42, these two need to swap. So then we bubbled the 76 up to the top, right? And then we just kind of keep going. And each iteration, we're going to bubble a different element up to the top. So then we go through again, 30 and 53, those are good. 53 and 29, those need to swap. Okay, 53 and 61, those are good. 61 and 53, swap those. Swap with the 14. Then swap with the 42. And so now we bubbled up the 61, right? Okay, so now we're gonna pass through again. Okay, 38 and 29, those need to swap. 53, nope. 53, nope. 53 and 14, these two need to swap. And then the 53 and the 42, those need to swap. Right? And so now we bubbled up the first 53. Okay, now we're gonna go through again. Don't swap, don't swap. Swap the 53 and the 14. And then swap the 53 and the 42. All right, and then we're going to pass through one more time, right? Okay, don't swap these. Swap the 38 and the 14. Okay, no more swaps. And then pass through one more time. Swap the 29 and the 14. And then we have our sorted array, right? So essentially what we did was each iteration, we bubbled up the 76, then we bubbled up 61, then the 53, the other 53, right? And every time we just bubbled up the next highest number until our array was sorted. Any questions about the bubble sort? Pretty straightforward. Okay, don't see any questions. So we're going to keep moving to selection sort, right? Characteristics of selection sort. Once again, my slides are not displaying super great. So basically we have best case and squared, average case and squared, worst case and squared. This can also be done in place. And is this stable? No, it is not stable. So selection sort, how does that work? So the next two sorts that we're going to be doing are pretty similar, right? Similar-ish, in that we build a kind of sorted portion of our array from the unsorted portion of our array, right? In selection sort, we essentially are like building out this portion of our array that is sorted, and each time we select the smallest element from our unsorted array and we push that into the sorted array. And that's essentially how we are going to do that. So let's go through an example of selection sort real quick here. So yeah, all right. So we start off selection sort. We have our unsorted array. And then we're going to start building the sorted portion from that unsorted array, right? So we start off, the minimum value that we've seen so far is 53. So we're going to pass through and find the minimum value, right? 38 is smaller, so that's our min. Keep going. 76, nope. 29 is smaller, so that's our new min. Okay, 61, nope. 53, no. 14 is smaller, so that's our minimum value. 42, nope. So then we're going to move our minimum value to the front of our array, right? So we move that over and we swap it with the 53. And now the golden potatoes, because I guess we're using potatoes for this example, represent the sorted portion of our array, right? So now we're going to go and pass through again the remainder of our array, the portion that is unsorted, and we're going to find the new minimum value. So start with 38, that's the min. No. Okay, 29 is the min. Not 61, not 53, not 53, not 42. All right, so now we have 29 as our new min. So we're going to swap that with 38. And then now our 14 and our 29 is our sorted portion, right? Golden potatoes. And then the remainder of our array is still unsorted. All right, so let's pass through again. 76 is our min. All right, 38 is smaller. Set that to the min. No, 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 no. All right, so move in 38, right? And we're going to keep going. 76, no. 61 is smaller. 53 is smaller. No. 42 is smaller. Let's move that in, right? Move the 53. So here, notice selection sort is not stable. Why is that? That's because the second 53, right? We just moved the first 53. The second 53 was originally at the beginning of our array, right? That it was at the first index where our 14 now is. But because we moved the 14, we swapped them. And so that's why this sort isn't stable, right? Because the 53s have now switched positions. So that's what makes this sort not stable. We're going to just continue our algorithm, keep adding the smallest element and building that sorted array. And then at the end, we end with our sorted array. So are there any questions about selection sort? Okay, don't see any questions in the chat, so we're just going to keep moving on to the next one, insertion sort. So insertion sort is pretty great one to use, particularly for lists that have been almost sorted. And if you're using an elementary sort, typically probably insertion sort is the one that you want to use. Stable, can be done in place, and for the most part is faster than the other elementary sorts, particularly if you have an array that is almost sorted or array that is like particularly small. So the basically gist of what we're going to be doing for insertion sort is just like with selection sort, we're going to be building that portion of our array that is already sorted. Except for in insertion sort, instead of selecting the smallest element, we're going to essentially just, each time we build our array, we'll take the next element and then we'll just move it into the proper position. We'll kind of shift it left into the proper position in the sorted portion of our array. So, and then we're just going to kind of keep building that section that has been sorted until we cover the entire array. So, once again, we have O of n squared, but this is typically going to probably run a little bit better. And I think it's going to be pretty clear from the example that we're going to show how that works. So here we go. We have our starting array, unsorted, right? This time we are being represented by ice cream instead of potatoes. And we're going to start to build our unsorted portion of the array, right? So we start with our 53, and we're gonna that's gonna now be our sorted portion, so to speak, of the array. And so we're gonna insert that into the sorted portion. Okay, so this has been inserted. Now we're gonna grab the 38, which is the next element, and we need to insert that in, right? So we're going to keep shifting left until the element to the left of the 38 is smaller, right? So we're going to shift left because 53 is greater, and then we're going to put the 38 in there. All right, next we have to grab the 76, and we have to push that into the array. So we're going to grab our 76, and we're going to keep shifting until we get to a smaller element. 53 is smaller, right? So we stop our shift right there. Okay. Next, we're going to grab 29. Once again, we need to keep shifting left until we get to a smaller element. So we're going to shift left once, again, again. We put it at the beginning, right? Next, we need to insert the 61. So we keep shifting left until we get to a smaller element. So we shift left once, and then we compare against 53, and 53 is smaller than 61, right? So we don't need to shift anymore, and we're going to insert it here. All right, now we're going to insert our next 53. So shift left once, shift left again, right? 53 is not smaller than 53, so we're just going to put it here. And this allows our array to maintain that original order that we saw, right? So these elements didn't have to be swapped. The relative order of the 53s was maintained for this. So then we're going to keep going. We're going to take the 14 and we're going to insert it into our array. So we're going to swap, 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 swap. And then we're going to push it at the end. And then lastly, we're going to do the same thing with the 42, right? So we're going to compare, 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 compare. And then 38 is smaller than 42. So we place our 42 and there it is at the end. So that's essentially insertion sort. Are there any questions about either of the three elementary sorts? Okay. If we don't have any questions, then I'm going to move on to merge sort. So merge sort is a somewhat more complex sort, right? Essentially, we are going to be recursive here, and what you do is you take the list, right? You split in half. You do that again and again and again, and then you just start to combine those. And the combining step is probably the most work for our merge sort, right? And that's where we're essentially going to take these two sorted arrays and we're more or less going to perform a union operation on them, right? Just like we saw last week where we're going to kind of walk a pointer across and then join the elements in sorted order. So we can see a quick example here, right? Where we have, once again, our unsorted array and now represented by puzzles. So we recursively break it down, break it down, break it down until we get to our base case where we've broken down each element into its own little puzzle, right? And for our base case, a single element is already sorted. So you don't have to do any more work there. So each of these elements in of itself is already sorted with itself, right? So then we're going to start to merge these back together. And so then kind of from the bottom up, each element is if it's represented as like a set, right? We're gonna kind of walk a pointer across and join these two elements. So we join the smaller element, 38, 53, right? And we're gonna join each of these two sets. All right, so now all of those have been joined. We have 4 sets of size 2, right? And then now we're gonna kind of go one step out and we're gonna start to join these. And the important thing for merge sort is that each of these little arrays now, right, mini arrays, is in of itself sorted, right? So each time that this is now sorted, we can essentially just go across it in O of n and join those two arrays. So we throw on the 29, 38, 53, 76, right? So we're joining those two, and then now we're going to join these two. 14, 42, 53, and 61. All right, so now we only have 2 arrays, right? Both of these arrays are sorted, and we just need to lastly merge these two together. So we're gonna walk kind of 2 pointers across, keep pushing on the smallest element, move across the arrays. And then we have our completed sorted array, right? So because merge sort is recursive, we can apply the master theorem to this, right? And then we are essentially splitting the array into portions, just like we did. And then we're calling the merge function on them, where the merge function is essentially just doing like a union operation. And so that's going to be O of n. And so that's why we have the T of n over 2 plus T of n over 2 work, right? Because we are sorting the left half and sorting the right half. And then we have to merge each of those. So essentially, we call master theorem on this, and that's what gives us our O of n log n complexity for merge sort. So here's a great thing for your cheat sheet. And are there any questions about merge sort? Okay, so I don't see any questions. But yeah, so the idea is merge sort, divide and conquer, recursive. The essential step is we're just breaking things down and then we're merging those two sorted sets together. And then we're usually going to have O of n because we usually use like a separate container for doing that merge step. We usually copy over into a second container and then we're going to copy back. So that's why we usually have O of n memory, right? Otherwise, this is stable, and n log n is what we're going to be typically going to see for a merge sort. All right, so I don't see any questions. So we're going to move on to quick sort. Quick sort is also going to be n log n. It is unstable, but is typically probably the fastest of the n log n sorting algorithms usually. So quick sort is a little bit difficult to understand, but we essentially pivot somewhere in our list. We sort, right, so that the left-hand side of the list, the left side to the left of the pivot are all elements that are strictly like smaller than the pivot, and then the right side of the pivot are the elements that are greater than or equal to the pivot, right? So you basically divide it like that, and then you recursively do this step again and again and again, and you keep pivoting, and then you keep kind of doing that sorting portion. So that's kind of how quick sort is going to work, and we can go into an example here. So for this example, we're going to choose the last element as our pivot, right? So the 42 is our pivot, and that just kind of makes life easier. And we essentially have two pointers, right? We have left pointer and the right pointer, and we're going to walk them kind of towards each other. And for each pointer, you have to check, okay, everything on the left side has to be less than the pivot. Everything on the right side has to be greater than the pivot. So if we have any instance where this doesn't occur, we're just going to swap those two elements, right? So the 53 is greater than 42, so we're going to have to swap that. The 14 is less than 42, so we're going to have to swap that. All right, so we swap these two elements, and then we're going to move our pointer, right? 38 is less than 42. That's okay. Okay. 76 is greater than 42. That's a problem. We're going to have to swap that. Okay, move our right pointer. 53 is greater than 42. We're okay. 61 greater than 42. We're okay. 29, that's less than 42. So that needs to be on the left side, right? So we're going to swap these two elements, the 76 and the 29, so that they're in the proper location. All right, so we've swapped those. And then after we swapped those, all right, we keep moving our pointer. And now we see that we've come to the end, right? Because our pointers are equal. So at this point, we take whatever element is left here, and we're going to swap that with the pivot. All right, so we swap this with the pivot, and then now the important thing, right, is we can see every element to the left of our array is not, or to the left of our pivot is not necessarily sorted, but they are all smaller than the pivot, right? And every element to the right of the array or to the right of the pivot are all specifically greater than or equal to the value of the pivot, right? And so then now we're just going to break the array down and we're going to call this algorithm again recursively. So here's our pivot. This portion is sorted. Okay, the remainder we need to partition, and then we need to run this again, right? So we're going to do this on the left side, and then we're going to do this on the right side. And it just calls recursively until we get to the end. So any questions about this example in Quicksort before we kind of go over some of these summaries? I know that Quicksort can be kind of difficult to understand. Okay, I don't see any questions in the chat, but if you think of anything, feel free to just drop it in the chat, and and I'll let you know. Worst case behavior is the smallest or largest element, right? Because we kind of want our element to be our pivot to be in the middle, right? We want it to be as close to the middle as possible. So if you have the smallest or largest element, you're moving that all the way to the middle. So you're going to just be doing lots of extra swaps, basically. So then conversely, the best pivot choice is the median element, right? Because that's going to get us our really good partition where we have to do significantly less swaps. So the median element is usually our best choice for quicksort, but it's kind of, you can't really choose the median element, because if you knew the median element, then your array would already be sorted, right? Because that's kind of the whole point of the array not being sorted, is you don't know what the median element is, because you don't know where it is in the array. So because we don't know where the median is, what we can often do to choose our pivot is we can use a sample, right? So you, like a common way you'll see this is you'll choose like 3 elements from the array just kind of randomly. And right, so it could just be like one end of the array, the opposite end of the array in the middle. And then you take whatever is the median of those 3 elements is what you'll choose. So you just kind of sample a median, and that allows you to kind of usually get a good guess. So then we have our summary page, just kind of great. This is a great table to just kind of copy down for our cheat sheet. Are there any questions about any of the sorts that we went over in this lab before we move on to binary search? You can feel free to drop in the chat, or you can even unmic yourself if you want to, unmute yourself if you'd prefer. All right, I do not see any questions, so I am going to move on. Hopefully that is because I have been incredibly clear and not because you guys are all hopelessly lost. So is anybody hopelessly lost? Okay, I don't have any yeses there, so that's good. I'm going to move on real quick to here. One sec. Just going to switch back to my slide so I can annotate things. Okay. All right, so moving on to the last section, we're going to be talking about binary search. Binary search, classic for interview problems, right? I think most of you at this point are familiar with binary search from, I think if you took EECS 280, we go over it a little bit in that. And just basically the idea of splitting an array or some container in half and then searching each half, right? So we're just going to look at a couple of example problems. Okay. So first example problem, you are given an array that is first increasing and then decreasing. Find the maximum value of this array, right? So like for this example, our input array, we have increasing, increasing, increasing until we get to 500. And then we can see that it's decreasing after that, right? So then the values start going down. So we would output 500. For this example, increasing, increasing, increasing 50, and then decreasing here, increasing, increasing, increasing all the way to 50, right? There aren't any elements after that. And then in this example, increasing up to 120 and then decreasing for the rest of the way. So how would we go about solving this problem? Spoiler alert, the answer is binary search, right? So how are we going to do that? We are going to obviously perform a binary search. We're going to keep checking the middle element. And we're going to have a couple of different cases, right? So like if we have an array here, like 3, 5, 1, say, right? If this is our array, we know, okay, if we check the middle element, it's greater than both of its elements. That means that this is the max, right? Alternative example, if the middle is greater than the element to its right and smaller than the element to its left, then we must still be in the increasing part, right? So if we had like this, all right, we check 5. 5 is greater than 3, but less than 6. So there must be a value greater over here. And then conversely, if we had like, right, if we had a situation like this, we know we're on the decreasing portion of our array, right? Because if we check the middle element and the value to its right is less, but the value to its left is greater, then we know that we're in the decreasing portion, right? And that means we need to check to the left. So basically we have 3 different cases, and we're just going to perform a binary search, and then depending on our situation, we'll just check either portion of the array. Well, actually, okay, so I guess they didn't give an implementation. Does this make sense to everyone? Does everyone kind of understand this example from kind of the slides? Any questions about this example? All right, quiet in the chat. So we're just going to keep moving onto the next one, right? But okay, you're given a kind of, this is kind of a pretty similar-ish question, right? You're given a sorted array that has been rotated, and then we want you to find the minimum element this time, not the maximum element, right? So if we're looking at this first example, this array was, we could have had this array was like originally 1, 2, 3, 4, like this. Oh wait, no, sorry, a little bit longer than that. 1, 2, 3, 4, 5, 6, right? And then it was rotated because we took the 5 and the 6 and we moved those to the front essentially. So then we now have the 5, 6, 1, 2, 3, 4. So it's asking find the minimum element in this array, right? Do we have any ideas? Let's see if anyone can drop in the chat. How about before we jump into this problem, any ideas of how we would go about tackling this? I'd love to see anything in the chat, just partly to make sure that everyone's still alive with me here. Same idea as the previous question, but the cases are different. Yeah, that's a really good way to put it. Pretty much, yeah. We have the same idea, right? We're gonna binary search this, big surprise. And in this situation, we don't have it, kind of similar, right? But the left side of the array is kind of increasing, but the right side of the array is also increasing, right? And what we find is we actually don't have to perform as many checks here. So for here, they have a whole lot of word vomit kind of telling us what to do. And essentially, we're going to keep checking the minimum, the middle element, right? And we're looking for an element that is less than the element to its right, right? Because our array, if we're looking at our example here, is strictly increasing except for at the point where we have pivoted, right? So the only element that is going to be less than the element to its left is going to be our minimum here, right? So for this example, I'll just kind of go through what our algorithm would do real quick. 1, 2, 3, 4. Right? First, we're going to check the 2, right? And we're going to check, okay, is the element to the left of the 2, because that's our minimum, our middle element, is the element to the left of the 2 greater than 2? No, because 1 is smaller than 2, right? Okay, in that case, the minimum has to be somewhere on the left or somewhere on the right, right? It's not this element. So if the element to the yeah, so if the, here's where we have to perform a few more checks. Right, we're going to check, okay, is the element here, our middle element, smaller than our last element, which in this case is the 4, right? If it is, then the minimum has to lie somewhere in the left. If it's greater than 4, the minimum has to lie somewhere on the right. We're going to basically just keep narrowing down here, right? So since 2 is smaller than 4, that means that we have to check the left side of the array, right? So we're just going to kind of, for terms of our search, we're going to more or less chop off this side of the array. We're going to look at the left side of the array, right? And then we're gonna keep doing that until we get to the location that we're looking for. So we're going to perform this again. 6 is going to be our middle element, right? We're going to check 5, 6, 1. Is 6 less than 5? No. Okay, so it's not here. All right, compare 6 to the last element. 6 is greater than 1. That means that this has to be, the element has to lie somewhere to the right, right? So we're going to break this array down one more time. Cut off this, and then we're going to check 1 here. All right, check the element to its left, which is the 6. 6 is less than 1, so this is the minimum element. All right, so we basically broke down the whole array, and then we looked at the left half, and then we looked at the right half, and then that left us with our solution. So any questions about this example? All right, I do not see any questions. So I'm going to move on to the next one. Again, somewhat similar, you're given a sorted array where every number appears twice except for one number, right? Except for one number. And then find the number that only appears once, right? So we have in our first example is kind of long, but we have 2 1s, 2 6s, 2 9s, 2 22s, 1 26, and then 30, 30, 40, 40. Right. Second example, kind of more manageable. We have 1 1, then 2 2s, 3 3s, or 2 3s, and 2 4s. Blah, blah, blah. And then third example, same thing with the 4. And then the last example, there's only one 281. So that's the 281. This one I think was a little bit less intuitive, so I'm just gonna go into the solution kind of. But essentially, if we consider an array that had only double elements, right? So like let's say we had 2, 2, 3, 3, like that, right? Um, we don't even have to really consider the fact that the array is sorted. What we need to look at is the indices, right? Because if we have an array with only double elements, this is going to be index 0, 1, 2, 3. We know that the first index for any given element is going to be even, and then the second index is going to be odd, right? And then if we repeat that for the next element, first index even, right? Because 2 is even. And then the second index is odd, right? But if we had a different array, so like if we have 2, 2, and then only 1, 3, right? And then let's say we had like 4, 4 on here. That element, the single element, is going to disrupt our indices here, is essentially the idea of how we're going to be tackling this, right? So for our first indices, so like 0, 1, 2, 3, 4. For our first indices, we have even, then we have odd, right? Then we have even, and then this one, the element is different, right? So this is going to be odd for our first element and then even for our next element. So from here on out, after we see our single element, we've flipped. So now instead of even odd, we have odd even for all of our indices, right? Because we have 3, 4, and if we had more elements, like say like 2 5s, right, we'd have odd, even, so on and so forth. So that's essentially how we want to go about this. Is we're going to search for the location where the indices flip, kind of I don't know, polarity, right? So we're going to search for the location where we start getting odd even instead of getting even odd. And then here we can pretty much see an explanation about that, right? So if there's no element, the first occurrence would be even, second occurrence would be odd, kind of just like we showed, right? And then once we reach the odd one out, the opposite is true. So basically, we're going to check our midpoint, right? And then if the midpoint is even, check if the value is equal to the next one. Otherwise, if the midpoint is odd, check if the value is equal to the previous one. And then if these are true, that means we're on the left half of the array, right? We have not reached our weird element yet. But once these conditions are not true, then we're in the right half of the array where things have been flipped for us. So yeah, so like if we were to do this example, it'd be pretty trivial, right? Because we would check this one, and that's our element right there. But we would essentially check if the values to its sides are equal to it, and it's not. But if we were to do like one of these larger examples, right, we would start like somewhere here in the middle. I think like here in the middle, right? And then we know, okay, we need to check to the right. So then we check over on the right side of the array. Oh, now we're on the right side of the array, so we need to check to the left, and then we essentially narrow down on the 26. So that's more or less how this example works. Are there any questions about any of these examples that we went over? Or any questions in general, really, because otherwise we're pretty much at the end here. We're just going to go over the handwritten problem. Okay, I don't see any questions, so I'm just going to keep moving. So this week's handwritten problem, little bit more of a difficult one. Essentially, we are given a vector with n elements, and specifically the elements are only equal to 0, 1, or 2, right? So there are only 3 values that these elements can take. And so you need to develop a O of n algorithm to sort this vector. So not O of n squared or O of n log n. And then there are more constraints. You have to do this in a single pass, right? So you can't even go over multiple times. It has to be one pass. You cannot copy items. You cannot create extra arrays, or do any other essentially memory things. So we have to have O of 1 memory pretty much. And then you have to make sure your algorithm works for all cases. You may use standard swap, that is allowed. So like if this is our example array, right? Notice we only have zeros, ones, and twos, which is pretty key for this question. And then where our algorithm is going to pass through this array once. Our algorithm is going to pass through this array once and sort it so that we have all the zeros, the ones, and then our twos, right? And so then that's going to be essentially the written problem for here. That's just the end there. For going over this, we don't really have like any slides for going over this week. The best suggestion I could give is, Google is kind of your friend here a little bit. There are some similar problems that you may be able to find that would give you a good idea for how to go about tackling this. I would never recommend just like copy pasting some code from the internet, because you never know if that's correct. And also we wouldn't want to have to hit you with an honor code, so we want you to do your own work. But I would recommend looking up some of the ideas that may be useful. You may be able to find a similar algorithm by a specific regarding a specific European nation. If I'm going to give any hints, that might be able to help out with this. So otherwise, that's pretty much it for this lab. Good luck on the exam. You guys can feel free to ask me any questions. I still have a bit of time left in my lab, so I'm just going to be kind of hanging around here. I'm going to stop the recording real quick. And yeah, otherwise, good luck. And yeah, that's pretty much it. So.